Hello, in this video, we will explore how to understand the mathematical concept of differentiation using the Go language. First, let's briefly look at what differentiation is. The derivative of a single variable function represents how the function's value changes with respect to the input value. More specifically, it refers to the rate of change of the function value with a small change in the input value. This is obtained through a limit. In other words, it measures how fast the function changes at a specific input value. Now, let's extend this concept to multivariable function. A multivariable function takes several variables as input and transforms them into several output values. When calculating the rate of change of a multivariable function, we think of the reference vector, denoted here as c, as the point of reference. In multivariable function, the direction of change is important. What is needed here is another vector, u. The directional derivative of a multivariable function is calculated by measuring how much the function value changes when moving slightly in the direction of vector u from the reference point c. This concept also applies to single variable functions, but here the variables are extended to multiple ones. Among directional derivatives, there is a special form called partial derivatives. Partial derivatives measures how the function value changes when only one of many input variables is changed. It is usually represented using the delta symbol instead of d. Now, let's think about how we can implement this differentiation in the Go language. A multivariable function can be thought of as a function that transforms multiple variables into a single real value. To implement this in Go, we need a function type and a vector representing the point. Although it could be implemented as an interface, we will define as a struct here. To calculate partial derivative, we need to take a small increment delta as an argument. Setting this value small allows for accurate measurement of the function's change. Theoretically, when we calculate partials, this increment should be an infinitesimal, but since we cannot actually use an infinitesimal in calculations, we instead find the rate of change with a very small positive number. However, the size of this small value is not fixed for every function, so it is better to take it as an argument for stability in calculation. In the implemented method, we can see that the limit definitions of directional derivatives is directly applied. Next, let's look at the gradient. In multivariable functions, the gradient vector consists of partial derivative coefficient for each component. These can be found by linearly combining each partial derivative value with the standard basis vector. In Go, the gradient can be implemented as a function that returns a vector. To compute the gradient, like with partial derivatives, we need a function that takes real number as an input, a point, and the delta required for partial derivatives. The gradient must return something that satisfies the vector interface, and this is created using the zero method of the vector. The zero method returns the zero vector. By vectorizing the returned zero vector and adding the term as shown above, we will build the gradient vector. First, we need to calculate the partial derivative coefficient for each EI. To do this, we need the standard unit vector to input into the partial function, and this is where the basis method of the vector interface come into play. By calculating the directional derivatives in each direction and multiplying them by scalar for each vector, we obtain the gradient vector. We will see how this works shortly, but first, let's expand on the concept of the gradient. When we talk about multivariable function, they often have multiple output variables as well as input variables. The derivative of a general multivariable function is a matrix. Each row of this matrix corresponds to gradient of a component function. Do not think of this matrix as just a list of partial derivatives coefficient. Instead, It is a function that transforms a vector into another vector. Let's explain this in detail. When a point C in the domain of a single variable function moves at a speed of x prime, the y-coordinate of the point on the graph moves at a speed of y prime. The derivative f prime c relate x prime and y prime, meaning y prime is approximately f prime c times x prime. Although the derivative f prime c of a single variable function is a real number, it can be thought of as a rule that connects the change in domain and codomain points. Let's apply this to multivariable function. Suppose a point P in the m-dimensional domain corresponds to a point Fp in the n-dimensional codomain. If P moves along some path, that path will also correspond to a path passing through Fp. We are interested in the instantaneous movement of the point P. Suppose P moves at a speed of v, and the point Fp in the codomain moves at a speed of w. The n by m matrix of DFP acts as a function that connects v and w. W is DFP multiplied by v. Therefore, the derivative can be thought of as a rule that predicts the movement of the codomain point based on the movement of the domain point. In this sense, let's think about how we can implement a function that represents differentiation. The differential function, which represents differentiation, takes f from the map interface, p from the vector interface, and delta as argument. What it returns is a function that sends one vector to another vector. Although the derivative of a multivariable function is a matrix, its function is to map a vector to a vector. Therefore, what we implement here is a function that uses information about the function to map a vector to a vector. When the vector interface variable v is input, we should return a vector of the same dimension as the point P. Therefore, first thing we do is using zero method of the vector interface for variable P to generate a zero vector. Then we store the result of multiplying the derivative of fp dfp with the input vector v. From the definition of the derivative, we can see that each component of this vector is the inner product of the gradient of each component function with vector v. Thus, we multiply the result of the gradient by the vector v for each basis vector and add them together. Now, let's test this. First, using the structure of two-variable function, we implement the function fxy equals to x squared plus y squared. The gradient of this function at the point 1 over 2, 1 over 2 is 1, 1. Testing this yields results that are nearly identical. Now, let's test the derivative. To implement a multivariable function that has vector values as output, we create a struct called multiple. We also define a map method to satisfy the map interface. This essentially performs the same function as multiple's eval method, but redefined to conform to the map interface. Through this, let's implement the following function. Point P is 1 over 2, 1 over 2. Since the output of differential is a function, we cannot print it directly. Therefore, we will print the result when the vector 1, 1 is input. Now, first, let's manually calculate this in advance. The derivative as a 2 by 2 matrix is as follows. Substitute 1 over 2 and 1 over 2 into this yields the following matrix, 1, 1, 1, and minus 1. And then multiplying this by the vector 1, 1 gives the following vector 2 and 0. This matches the test result. For reference, the e minus 11 at the end means 10 to the power of minus 11, so it can be considered as 0. In this video, we have implemented the concept of differentiation as a function that takes an interface as an argument. In the next video, we will cover integration. Thank you.